these. So if you want to come back and look at the why of these answers, you can go back and review these if you choose. So I've chosen the problems at the end of the chapter that I think are the most relevant. These are the ones that are also very similar to the problems that you'll have in Master Chemistry, or at least a few of them will be. So the first one is problem number 36. I say, or the question asks, determine the types of intermolecular forces present in each one of these elements or compounds. And just to review the possibilities that we have dispersion forces, have dipole-dipole forces, you have super dipole or hydrogen bonds, and then you have ion dipole interactions. So there's 4 possibilities that we could put on these things. Okay, so what would I put as answers for these guys? So the first one, anything that's monoatomic, it's not going to have a dipole. So if it's just one atom by itself, the only thing that it can have are dispersion. So this one's anything that's monoatomic, one atom by itself, is going to just have dispersion forces. And that's true of diatomics as well. All right, so diatomics, that would be the same thing. So if it's something like, example, N2, the only type of forces it's have are going to be dispersion. Okay, so let's look at the next one. Let's look at NCl3. So what I need to know now is what's the Lewis structure, and then I need to know how the charge is separated out in that compound. So nitrogen is something that its common bonding patterns, it wants to have 3 things bound to it, and it's got a lone pair of electrons. All right, so it has 3 things bound to it, and there are 3 chlorine atoms in this case that are bound to it. So if I look at this guy, that's go back to the Vesper, that's an AB3E. That's a trigonal pyramidal is the type of molecular geometry that we have with that. And if I think about what are the values for the electronegativities, to think about where the dipoles are going to go. So nitrogen, so 4, 3.5, 3. Nitrogen's 3. And chlorine's also 3. So there's really not the fact that there's much of a pull in the electron density away from one and the other. Where the pull comes from is the influence of this lone pair of electrons. Okay, so there is going to be a little bit of a dipole moment introduced by those electrons being there. So if I look at the type of interactions this one can have, everything has dispersion. So dispersion force is number 1. The second one is it's going to have dipole-dipole interactions. Right? If I look at the next one, right? If I look at silicon tetrahydride, so there's 4 hydrogens on it. Silicon is underneath carbon in the periodic table. So remember, the trends is that everything wants to be just like everything in that group. So what's above silicon in the periodic table is carbon. And carbon wants to be found with 4 things bound to it. No lone pairs of electrons. So that's the way silica is going to be found. So if I look at its formula, and if I try to represent it in 3D, it's a tetrahedron. So I've got 2 in the plane, and I've got 1 going back into the board, 1 coming out of the board. Okay, so, but now all the atoms are equivalent, and I've got symmetry associated with this, and because of that, all of the polar bonds, even though there's a difference in electronegativity that is pulling from the silica to the hydrogen in each one of these, those things are the small difference in electronegativity are going to completely cancel out because of the symmetric nature of this. So it is a nonpolar molecule. So that means it doesn't have dipole interactions. So the thing that it does have, though, is what all molecules have. It has dispersion forces. Okay, so dispersion. All right, we'll do the last example, last one. So if we do D, I've got HF. So I know that everything has dispersion, so it's going to have those. What can you tell me about HF? Hydrogen. If it's fluorine connected to a nitrogen oxygen, or hydrogen connected to a nitrogen oxygen or fluorine, it's fluorine in this case, it's the H bond. So it undergoes hydrogen bonding. Now, if you said hydrogen bonding is dipole-dipole bonding, that's true. It is. It's just a especially strong type of dipole-dipole bonding. Okay, so that's how you would answer those. You got some answering chemistry questions just like these.
So would HF be all three of them? Like if in an answer, would it be dipole-dipole H bond or just H bond?
Just H bonds, typically the way we're going to answer it. So that's what I'm saying. In all truthfulness, it really is dipole-dipole. It's just an exceptional type of dipole that we characterize by itself. Okay. So if somebody gave me that as a test question and the choices were the three, and you might have an argument that those are the same thing. But since the book distinguishes them as separate categories, that's the way that we break it up. Okay, is the 4 different types. Okay, so this is another group of compounds that do something similar. So same type of questions here. Okay, so let's start with the, we won't do all of them, we'll do a few of them. All right, let's figure out what this guy is. All right, so what is its geometry?
3 things bound to the B and then.
Okay, exactly. So it's just going to be like nitrogen. Right, so if I look at it, it's going to have a lone pair and 3 things bound to it. All right, so if I look at that one, it's going to be a similar type thing. There's going to be a dipole moment because of the lack of symmetry. There's going to be a dipole moment pulling in this thing. So it's going to have dispersion forces. It's also going to have dipole-dipole. Okay. All right. What about B, HBr? So you've got monoatomic or diatomic, 2 atoms attached to each other. It's just 2 atoms. It's not 2 of the same atoms. If I look at the difference in electronegativities, I don't know what bromines is off the top of my head, but I know it's greater than hydrogen's 2.1. So y'all could look it up. It's maybe 2.7, 2.8, something like that. That means that there's going to be a charge separation. There's going to be a dipole in this compound. So that tells me that that one's going to have dispersion forces as well as the dipole-dipole. Can it H bond? No, because it doesn't have a nitrogen, oxygen, or fluorine. Okay. Let's do the last one. Let's do this guy. So this is methanol. And the structure of methanol, if you just kind of work out, the formula gives you an idea how things are connected. The fact that the 3 carbons or 3 hydrogens are next to the carbon tell me they're all connected. And then the O connected to the carbon connected to the hydrogen. This type of a group is called an alcohol group. Right? So everything has dispersions. Okay, if I look at the different portions of the molecule, this has an electronegativity of 2.1. This is 2.5. Oxygen is 3.5. This is 2.1. So if I look at the section to the left-hand side of it, all of this portion of it is nonpolar because the difference in electronegativity in those bonds are less than 0.5. But I have to consider the other side of the molecule as well. So now if I consider the right-hand side of the molecule, here I've got a big separation. The difference in electronegativity is 1.4. So that means that there's definitely going to be a dipole created with this. So there are dipole forces present, but is there a hydrogen bond?
Yeah.
Because the hydrogen's connected to the oxygen, the way that those are H bonding. Okay, so, and again, H bonding is a type of dipole-dipole, but it's a recognition that it's a particularly strong one. Right? Let's do the last one here. The green, just for the heck of it. So let's do this diatomic. So I got I2. So anything connected to itself, a diatomic, because the electronegativities are going to be the same, one doesn't have a pull greater than the other. So anytime you have a diatomic, it's just like a monatomic, the only thing that you have are dispersion forces. Okay, so just recognize that. It'll make life easier for you. Okay, so another type of question, we did something like this in lab. I want to try to put these things together based on their boiling points. So to kind of do that, I need to know something about what are their geometries and what are the intermolecular forces that are occurring. Now these are all things that have hydrogen connected to them, and if I look at the element that varies, right, the sulfur, the selenium, and oxygen, they're all members of the 6A family. Okay, so being in the 6A family, they're all going to have the same geometry associated with it. So every one of these has a geometry. So element X, whatever it is, of an AB2, E2. It's got two lone pairs on it. All right, so that's a tetrahedral bent, or what we call the bent geometry. So because it's bent, if there's a dipole moment when these things, they're all going to be pulling in a way that it cancels out left and right. Those two things annihilate each other. But both of them have a down component associated with them, so there's going to be a net dipole moment in the down direction. Okay, so all of these have an electronegativity difference, so they're all going to be polar. They have that characteristic. Okay, is there something that sets any of them apart to be different from the others? Okay, so in water, if the oxygen's connected to the water, that's the H bond. So where the other ones have dipole-dipole, so dipole-dipole interactions, this one has super strong dipole-dipole interactions. All right, the stronger the interactions, the greater the boiling point is going to be. So the one that has the highest boiling point is going to be water. Okay? So now I have to figure out what's next. Do you think it would be the sulfur hydride or the selenium hydride? Okay, so the only thing that differs on these two things are the dispersion forces. And the dispersion forces are largest with the things that have the most electrons. Okay, so you go to the biggest atom. Selenium is larger than sulfur. So selenium is going to be a little bit higher than hydrogen sulfide. And to give you an idea, this one's definitely a gas at room temperature. This one's a gas at room temperature, and we know water is a liquid. This is our common rotten egg smell. Okay, that's what we associate with. That's the gas that's produced whenever you have a rotten egg. Question on any of those? Okay. Just looking at these pairs, choose the one that's going to have the higher boiling point. We'll talk through these, try to figure them out. So the first one has NH3. So NH3 is an AB3E1. So it's a trigonal pyramidal versus methane, CH4. We said was tetrahedral. Okay, we've already done something like that. So in the tetrahedral, there's symmetry. Okay, so the fact that the symmetry makes this one a non-polar compound, where this one there's definitely going to be a dipole moment that's going to be heading in the down direction. So, oops, wrong way, in the up direction towards the nitrogen. So this one is definitely a polar compound. So things that can interact more strongly, if it's polar, it's got both dispersion forces and dipole-dipole. So the one that's going to have the higher boiling point is ammonia in this pair. All right, we'll do the next one as well. Okay, so let's look at these two. So sulfur and oxygen are in the same class. So if you remember what CO2 was, or in the same family, CO2 is linear. That tells me that carbon disulfide is linear as well. Okay. So what happens with these is they both have dipole moments between the carbon and the oxygen, or between the carbon and the sulfur. But the fact that there's symmetry in they're linear means that they both annihilate each other. So the only type of forces that I have in both of these are dispersion. So I only have dispersion forces. So now I've got two things that only have dispersion forces. Which one's going to have the highest intermolecular forces and the highest boiling point? Look for the one with the highest molar mass. Okay, so the highest molar mass, if I look at it, sulfur is heavier than oxygen. So the carbon disulfide is going to have the higher boiling point. Okay, one more. So we talked a little bit about vapors just starting on this, and it wants to know which one has the higher vapor pressure. So we started talking about vapor pressure. The way that you formed a vapor molecule is you had to get enough energy to break all the bonds around it. That's kind of where we are in the notes. So the one that has the lowest intermolecular forces, so the lowest intermolecular forces yields the highest vapor pressure. That's the way we would answer this problem. We want to look for the one now that has the lowest intermolecular forces. It's going to have the highest vapor pressure. And we'll talk about that in class as we go forward. But I wanted to give you one more that you could do dealing with mastering chemistry. So if I look at this first one, as an example, I've got methane. We said a while ago it's a tetrahedral. It's symmetric. They're nonpolar bonds, so the only thing there you have with it are dispersion forces. But if I look at its cousin here, it's also tetrahedral, but it's not symmetric because they're not all the same atoms. One of the atoms is the chlorine, and the chlorine has electronegativity of 3. Hydrogen's 2.1, so that causes it to have a dipole moment in this direction. Okay? So that means that this one has both dispersion forces as well as dipole-dipole interactions. Okay, so now what we want to do, the one that has the fewest intermolecular forces, the one that has the fewest that's attract each other the weakest is the one that's going to form the most vapors. It's going to be the methane. All right, let's do B as well. So if we look at B, the two things with B are propanol. So if I draw the structure out for propanol, there are 3 carbons in it. Seeing it right? Yep. Versus methanol. We looked at this one just a moment ago. Okay? Now, we know everything has dispersion forces, so we'll label that on each of them. So this one has dispersion. This one has dispersion. Can we say anything about, would one have more dispersion forces than the other? Is one substantially larger than the other one? Yeah, the bigger one's got more surface area, more contact you have, so this one's going to have the greatest dispersion forces. This one's going to be lower. This much smaller. Now they both have another thing that's common to them, and that's the OH bond. So they both have hydrogen bonding, but that's common to both of them. It's not unique to one over the other. So they both can hydrogen bond. The thing that makes them different is the dispersion forces. So the one that has the highest dispersion forces is going to be the one that interacts the most. We want the one that's the lowest. So this guy is going to be the lowest intermolecular forces and have the highest vapor pressure. Okay. So the way that you would see this is that if I had some propanol, and if I spilt some propanol out on the counter, a milliliter, and I spilt some methanol out on the counter, a milliliter, if I come back in a minute, that methanol is evaporated. Even though it's a liquid at room temperature, as soon as you get a high surface area, its vapor pressure is very low, and it quickly goes into the gaseous state, where that propanol would take an hour to evaporate. It has a much higher boiling point, and it's much, much slower to go into the gas phase. Okay, so the other problems we got to cover a little bit more in class before we can go further than that. So next Tuesday, we'll finish up the rest of the problems for Chapter 12. Okay? And your Mastering Chemistry assignment is scheduled right behind that. I think I have the Mastering Chemistry assignment due on Wednesday. Okay, that's the goal behind it. Okay, so no, your I take that back. Your Mastering Chemistry, this one's split into Part 1 and Part 2. So when is the first assignment due?
Wednesday.
So Wednesday isn't tomorrow? Okay, so yeah, it's dealing with all of these topics. Okay. All right. So I'm going to stop that.